this slide because Simon asked actually a good question. I was too fast, and now I mean I wasn't wrong, but I was too fast, and I want to correct myself a little bit in order not to have some apparent inconsistency. So I did this slide about the support set, and it is important because support set is what determines essentially the factority of wave function. And what I said, that the support set is the minimum set of sites, such as the deviation from unity in the normalization sum is an arbitrary epsilon. And the beginning of analysis is that this function f of 5 should suppose that we have this function, and then this was written last time, so it is not changed. Essentially, what is written here is the following. So this is the distribution function. So if I integrate the distribution function from 0 to some alpha epsilon, this means that I compute the probability of psi squared, which are from maximum equal to 1 till some value. So then this is the probability. If I multiply the probability by the total number of sites, then there will be the expectation number of such sites with the amplitude larger than n to minus alpha epsilon. This is a normalization integral which is almost 1, so it plays not an important role. And then what I essentially do, I cancel this minus 1 by this n, and so I have in the numerator this thing. And then so this is S of epsilon, expectation number of S of epsilon, and the epsilon itself is the following, that what stays here is the expectation of psi squared. I mean the probability of having psi squared from very small number, practically, I mean 0, to some number which is n to minus alpha epsilon. So it is the probability to have small psi squared, and this small psi squared, which are not included in this sum, they lead to the deviation of the sum from unity, and therefore this thing is just equal to epsilon if I divide it by the normalization integral, which is the same. This one and this one should be the same in order to have a conservation of probability and the normalization sum rule if I take all the terms. So there are two equations, this one and that one. And then to evaluate this equation, I told you last time that if there is a big number here, it is supposed to be a big number, although in practice when you do some numerical exact diagonalization, it is not very big. But here I do the asymptotic analysis where this thing is big. Then such integrals essentially are given by two contributions. So one contribution is the contribution of the saddle point, where the thing which is in the exponent takes an extremal value, or this thing in the exponent takes the extremal value. So this is a contribution of alpha naught and alpha 1. And then there is a contribution of the end point, because it is the integral from something to something. And then everything depends which contribution is bigger. So if, for instance, as it is shown here, alpha epsilon is smaller than alpha naught, but larger than alpha 1, then this end point here and here, it will give the main contribution, and therefore this epsilon will be this exponent computed at alpha epsilon, and this one will be the exponent also computed, but different exponent computed with at a point alpha epsilon. And then we have two equations, and this is something which we had exactly in this form last time, but then I was a bit too quick. So so we have to look at this equation and resolve this equation to find alpha epsilon as a function of epsilon. So in order to resolve it, I just take the logarithm of both sides, and then I take into account that as n goes to infinity, alpha epsilon goes to 1. So it follows from the following: when epsilon becomes very small, then actually it is seen from this equation. You will see. So what I do, I just take the logarithm of this, logarithm of that, and then take into account that alpha epsilon is close to alpha 1. But then we know that this plot of f of alpha minus alpha, it has a maximum equal to 0 at alpha 1, and close to maximum it is quadratic. Therefore, I just write that this guy is simply quadratic in alpha epsilon minus alpha, and this is it. So if I take the square root, take the logarithm, and then take the square root, I will get an approximate solution of this equation when either actually in the limit when n is larger than this guy. So there is a competition here between logarithm of epsilon. Epsilon is small. Absolute value of logarithm of epsilon is large, and logarithm of n is also large. And then this, of course, is valid when logarithm of n is larger than this logarithm of epsilon, but it is quite a wide region of applicability of this formula. And then what I do, I just put alpha epsilon here, and of course here there is a coefficient. I will restore it now. I will restore this coefficient, and so what I will obtain? I will obtain that alpha epsilon to the leading approximation is alpha 1, and then there is a correction. And then I have shown to you that alpha 1 is equal to d1. So this leading term I separate, and all the rest I denote as some coefficient that depends on epsilon and depends on f. And when I substitute all these things here, then I will get this S of epsilon in this form. So this f second derivative of at a point of alpha 1 is what stays should stay here, because this thing squared times the second derivative over 2 is exactly this thing by expansion. So this guy is the main thing, and this second derivative divided by 2, it is simply expansion of the alpha in alpha epsilon minus alpha 1. And so I have this thing. So last time I omitted this factor whatsoever, and then soon noticed that something is not in order, because if you delete this formula, which was only epsilon here, then when epsilon goes to 0, S of epsilon goes to 0, 2, and it should go to the opposite direction. So this factor, which is very easy to get, it corrects this nonsense. Because if I take this formula and plot it, then what I will get, literally, I will get as a function of epsilon. As epsilon decreases, this coefficient increases. But then it reaches a maximum and starts to fall. So this falling part is what was the only one which I have shown last time. But in fact, as I also noticed last time, when it starts to fall, this formula is no longer valid, because this alpha epsilon becomes larger than alpha naught, and all this calculation become invalid. So, and therefore, what should be done is this: that this formula is valid until alpha epsilon is smaller than this point and smaller and bigger than that point. And when this condition is violated, then we should then actually the main contribution in these integrals will be given not by the end point, but by the fixed point, by the saddle point. And then, as I have shown last time, this S becomes 1, because f of alpha at this point at this point is equal to 1, and therefore S epsilon becomes just n, which is the maximum possible number. And so this formula is valid until it reaches a maximum, and then it should be 1. Not 1, but equal to n.
Vladimir, did you mention last time that in in a multifactorial case, this f functions should also depend on n?
Yeah. So what I'm saying is the following. So this f function you can define not only in the multifactorial case. You can define it in any case, even for Porter-Thomas. So if you have Wigner-Dyson statistics, then we can define formally this f of alpha and n in terms of the distribution of logarithm psi squared. So when if you have any distribution of logarithm psi squared, even if it is not multifactor, then I can formally define such an object. So it is, it is simply certain parameterization of this, certain representation of this distribution function of log of psi squared. So in general, f of alpha is a representation of the distribution function that you should, distribution function of log psi squared, that you should understand. So when I'm talking about f of alpha, I'm talking essentially about the distribution of the log of psi squared. So this is just another representation of this distribution. So if you have Porter-Thomas, then what will happen? I know the Porter-Thomas, then I plug it into here, and what I have something that depends on n. So if n is finite, then you have something which is like an inverse parabola, but in fact it is not a parabola, it is this function. And then, but what is important is that if it is a Porter-Thomas, so it is an ergodic situation, then there are two things. First, maximum is exactly at 1. And second is that the width of this parabola becomes smaller and smaller as n increases. And when n goes to infinity, it becomes just a straight line from situated at alpha equal 1 and going to f of alpha is equal to 1. So if I take Porter-Thomas, then when I take the limit n to infinity, I have a singular f of alpha. So you may call it f of alpha, but it is singular. If I have a fractal case, then what happens is that when n goes to infinity, there is some stable, non-trivial, smooth function. And this is the difference between the ergodicity and fractality. Because what means such infinitely narrow function? This means that your typical value of psi squared, which is n2 minus alpha, and alpha takes only one value, which is a unity. This is n2 minus 1. This means that almost in all points you have psi squared, which is 1 over n. And this is what, this of course is up to de Broglie oscillations, because if de Broglie oscillations are taken into account, then only this branch will be like the red curve, but this branch, which corresponds to small values of psi squared, it will be a power law. And why it will be a power law? Because there is a big probability to have zeros because of these oscillations. And if I average over de Broglie oscillations, average psi squared, or with de Broglie oscillations, then these zeros will be eliminated because, for instance, average of cosine square is 1/2. So cosine square has many zeros, but if I average, there will be 1/2. And since I eliminate this these zeros, then this curve will come to this point, and the distribution will be symmetric. So usually when we are talking about multifractality, we are not talking about de Broglie oscillation. So we have to get rid of them. For instance, we can say that psi is equal to de Broglie oscillations of Gaussian ensemble times some envelope function. And this you can do numerically. This we did in 2014 when we studied the f of alpha for random regular graph. So such things you can implement numerically. So what I'm saying is the following: that if you have a fractal phase, then n goes to infinity, you have some function of alpha, which is not singular, and this tells you that on the level of on the scale of logarithm psi squared, because alpha is essentially logarithm psi squared, the distribution is broad. And if you have Porter-Thomas, which is not fractal, then the distribution in this limit becomes infinitely narrow. I mean narrow when n goes to infinity, narrow on a scale of alpha. And that's why this definition of f of alpha, because what it does, it gives you explicitly the shape of the limiting distribution, which then determines all the fractal dimensions and things like that. So this is the thing. So what
Vladimir, probably you mentioned it, but how does it look for a localized system?
For localized system, I will. It depends on the localized system. So you see, the thing is that again. Okay, so I will answer it. It's an important question. So Lizzie, you understood. So this is a formal rewriting of the distribution. Mm-hmm. And then the thing is, what is the limit when n goes to infinity? Okay, then I'm asking you a question because it is important. So the thing is that, as I said, there is the support set, and the support set for the localized wave function must be not extended. So this means that d1 should be equal to 0. Otherwise, there is a support set which is extended. So this is the main definition. The main definition of the localized state is that d1 is 0. Now, but then you can imagine different shapes, and so, for instance, you can imagine f of alpha like this, which is, as I said, f of alpha on the lattice, alpha on the lattice is always bigger than 0 because psi squared is n2 minus alpha, and the sum of psi squared is equal to 1, so each psi squared should be smaller than 1. And then alpha should be bigger than 0. So this is the sum of the sides. So at any side, psi squared on the lattice is smaller than 1. And then alpha is bigger than 0. So if you take Anderson insulator, so the Anderson model insulator in 3D, then what happens that f of alpha will be like this. It will be also a singular thing. So it will be 0 here and minus infinity there. So then why so? Because how we determine d1? We determine d1 in the following way. We make a tangential to f of alpha with slope q equal to 1. And then when this tangential hits y-axis, it is minus tau. And then, of course, if d1 you have to take some epsilon we have already, some small deviation from 1, then you have, if you have small deviation from 1, then your tangential will be like this. But important thing is that if you take q a little bit bigger or a little bit smaller than 1, the tangential will be always passing through this point. Because, whatever you do, you have to do a tangential. And it always passes through this point. And this means that tau q is equal to 0. And all dq is equal to 0 when q is greater than 0. So this is, but then I told you that any f of alpha should have a maximum which is equal to 1. Here one should understand it in the following way, that you have an infinitely small slope. And somewhere in the infinity, this thing will be 1. But this is the limit. For any finite alpha, so this unity is reached at infinity, at alpha equal infinity. So this tells you that there are all arbitrary small psi squared, apparently because you have exponential localization and there are arbitrary small psi squared in the localized space. So this simply tells you that the usual f of alpha, we say that there is a maximum which is equal to 1. For a localized case, it is somewhere in the infinity, but this is how f of alpha looks like for the Anderson insulator in, let's say, 3D case, 4D case. But then recently, because of the many body localization, people start to think about localization on different graphs. So for random regular graph, Cayley tree, some other graphs. And this becomes an agenda because the Hilbert space in interacting system is certain graph. And therefore, the simplest graph that we can think of is a Cayley tree. It's irritating infinitely. So the simple graph we can think of is a Cayley tree or random regular. And in this case, f of alpha. So this is Anderson. And this is Anderson model, let's say 3D or 4D, any finite d. But then we can take a Cayley tree, and we can say that Cayley tree in some sense d equal infinity. What happens? What happens is the following, is that there is, in this case, f of alpha looks like this. It has a finite slope. in the Anderson case, it has zero slope, which is infinitesimal. And on the KT, it has a finite slope, and then the finite end point. So then this unity is reached at a finite point of alpha. And this slope, this behavior is linear, so f of alpha is equal to k times alpha, and this k is smaller or equal to 1/2. So at the critical point, okay, if it is insulated, then smaller than 1/2. At the critical point of Anderson transition, it is 1/2. So this is how Anderson insulator looks like. What will change for fractal dimensions? For fractal dimensions changes the following, that if I take the tangential with q is bigger than 1/2, if I take a tangential with q is bigger than 1/2, then, or actually bigger than k. So this is k times alpha. If it is bigger than k, then it touches f of alpha at this point. And then tau of q is equal to 0 when q is larger than k, and this k, and k is smaller than 1/2. So this is of course something like 1/k, this point. This means that the fractal dimension dq, which for this case is always 0 for all q greater than 0. For the Anderson model on the KD tree or random regular graph, it looks like this. So there is 1, there is k, and for all q greater than k, it is 0. But if q is smaller than k, then it is like this, and at q equal to 0, it becomes 1 as it should be. And important, why I am talking about that? I am talking about that for the following reason. That what is common in these two situations, why I call this insulator and this insulator, this localized case and this localized case. Because the fractal dimension d1 is equal to 0 in both of the cases. So, you know, what happens at small q is a different story. But important is that the support set is equal to 0 in both cases. And then you can think of any situation. You see, suppose this is 1, this is some, if this is 0 and this goes somehow like this, I don't care, this will be also insulated. And so this is the story. So insulator is different, f of alpha for insulator is different for Anderson case and for KD3. When this KD3 becomes like this, when this K goes to 0, and when it happens when disorder goes to infinity, then K goes to 0 in this case. So also on the tree, I can make this f of alpha lying on the axis, but it is only when disorder is infinity. Whereas for finite dimensional case, it is lying on this x-axis even for finite disorder. So this is This is the story. But you know, in this zone which I described you should have some navigation, and this navigation tool is D1. So if D1 is 0, it is localized case. And that's why I am investing so much time to this slide. Okay. Then I finished with that. So I told you that with this additional coefficient, everything is fixed, and your support set with decreasing epsilon, it grows, and then eventually reaches the maximum value of n, and then stays at this value. But then one can do the following: one can take the logarithm of support set and divide it by logarithm of n, and this gives you sort of running exponent which power of n stays here at a finite n. And what you see, it is again from this formula, but now I plot it as a function of the logarithm of n. And so what happens is that when n is very big, but not infinite, so like logarithm equal to 20, the deviation from D1 is big. So D1 on this plot is 0.65. And what you would observe having logarithm equal to 20 will be something like 0.86, 87, something like that. So it is a big deviation from D. And only when your logarithm of n becoming enormously large, then it reaches 1. So what this thing is, in some sense, it is an asymptotic, I mean, not in some sense, it is an asymptotic formula. So when n goes to infinity, this constant reaches some limiting form. But only when logarithm goes to infinity. So let's say logarithm 500, logarithm 1000, then you really have this thing. But in any realistic, for exact numerics, exact diagonalization numerics, you have very big deviation. So this is like a concept. It is a good concept. It is a concept that allows to say where you have localized case, where you have a non-localized case. But as a means, as a tool to compute D1, it is very bad, because it is converges to this D1 very slowly. And you understand why, because it is also an exponent. So it is an exponent, of course, of square root of logarithm. If it were an exponent of logarithm, then you would have change in the exponent here. It is not. It is slower than changing the exponent here in the n equal infinity limit, but still it is very significant. Okay. So then since Lisa was not here, I repeat a couple of trivial things. So one trivial thing is what is d at q equals 0, and so what you have to do, you have to take the tangential with slope 1, and then it hits the maximum, and we know that the maximum is always at 1, and so you obtain minus tau of q equals 0 is equal to 1. So tau of q equals 0 is minus 1. In order to find fractal dimension, you have to divide by q minus 1, and so you have unity. So this is an exact unit. So whatever happens at q equals 0, you should have fractal dimension equal to 1. But again, here it is reached in this way, in a regular way, and here it is reached as a jump. So it is 0, 0, 0, and then jump. So this is one trivial thing, and the other trivial thing is when this slope is infinite. So when this slope is infinite, then I mean, here I cannot plot the infinite slope. I need that it is big. And then, if your f of alpha has exactly some limit which is such that it goes to minus infinity and doesn't exist in this, so in this region, so it has a gap which is alpha infinity. Then it is easy to understand that when your slope goes to infinity, then this I mean at finite at b, this minus tau q is minus this alpha infinity times q, and so d1 is like this. When q goes to infinity, it is alpha infinity. So this means that there is another trivial fractal dimension which is d infinity, and this gives you this is a non-trivial value if there is a gap. If there is a gap like this. So then I told you that if you have a regular fractal f of alpha, but the part of f of alpha where it is negative, it is rare events. And therefore, if you do one realization or few realizations, you will not see this part whatsoever. You would think, you would not find so big psi squared, which corresponds to this part, or so small type psi squared, which corresponds to that part. And therefore, if you do several realizations, you will feel like it is minus infinity here, and then you will also have some typical minimum and typical maximum like this. But the difference with the previous slide is the following, that when you increase the number of realizations more, so you catch all the rare events, and you will see that there are psi squared bigger than the minimum or smaller than the maximum. Whereas in this case, it is exactly, there is nothing here. So that's the point. So then essentially a new thing. A new thing is the following, that there is a mysterious symmetry of tau q or f of alpha, which is which actually first was observed by in '89 in the work by Altshuler and Prigodin, but they somehow noticed the symmetry, but did not make far-going statements from that. And then it was rediscovered by Milin and Fedorov in 2004, 2005, and the thing is that if I write tau q, where again tau q is when the tangential hit the y-axis. If I write tau q like the tau q for ergodic case, plus some everything else, then this everything else has a symmetry for 3 Dyson symmetry classes. It has this symmetry. So first it was discovered for 3 Dyson symmetry classes, and this symmetry holds. What does it mean? It is very very dramatic and I would say mysterious symmetry, because it tells you that tau q and f of alpha, tau q for big Q and for small q are related. And so this means that this part of f of alpha and this part of f of alpha, so they are not arbitrary, they are related. This symmetry was derived as a mathematical consequence of the sigma model again, and then people who are very good in topology and things like that, because sigma model has a field which has certain topology, and this topology depends on the symmetry class. Then I told you all these 10 symmetry classes, then the Q matrix is different for all these 4 symmetry classes. It has different topology. In this language of differential geometry, it is some coset, blah blah blah. I don't want to go into this, but it was. It is possible to look at the topology of this Q matrix to derive this symmetry like this. But then, we are physicists, and physicists ask the question, where is it from? And this question is still mysterious. Nobody knows where is it is from. What deep properties of quantum mechanics they represent. So this is it is known for at least 20 years, and during these 20 years, mathematicians went forward and explained to us how does it related with topology of Q field and blah blah blah. But this is mathematics. What is we used to the fact that mathematics is important, but also important are some physical pictures why it happens, and this is absolutely not known. Now, okay, so it is not known, but let me do the following. It is some exercise. Also, Simon asked at some lecture how to come from tau picture, Q picture to f of alpha picture, and now I will be using it. Suppose this is known, how will it look like for f of alpha? And this is quite a simple exercise. So it would be there are 2 steps. So one step is that this symmetry means that it is a symmetry with respect to Q equal 1/2, because if this is true, then the delta is symmetric to about 1/2. So I introduce a new Q, which is like this. Then this symmetry would mean symmetry of Q and minus Q, like this. Next, I rewrite this in terms of this new Q, and get the following in these new variables out of this one, and then the inverse Legendre transform. So what one should do, one should take a derivative with respect to q, say that it is alpha, and solve this equation. When you solve this equation, you will find q of alpha. And then you put this q of alpha into the formula which I gave you before, that f of alpha is alpha times q minus tau q. So you just plug it to here and you have an f of alpha. Now let me do this manipulation. So first I have to take a derivative. Since q and q are just different by a shift, so differentiation with respect to q and differentiation with respect to q capital is the same. And then what I will get 1 minus, this is differentiated with 0, and this is the. Now, this is already almost everything is done, because as I said, delta of q is equal to delta of minus q. When this means that it is an even function. If I differentiate an even function, I will get a knot function. So this is a knot function. So what means that means that alpha minus 1 is a knot function of q. And then what I have to do, I have to simply rewrite f of alpha like this, and take into account that when I change 1 minus. So what is important, that alpha minus 1 is odd in Q. So what does it mean? It means that if I take minus Q, I have 1 minus alpha. And then what is 1 minus alpha? 1 minus alpha is how 1 minus alpha and this thing are related if I want to deal with f of alpha. If I have f of alpha, then if I replace alpha by something which makes 1 minus alpha out of alpha minus 1, so this means that I have to replace alpha by 2 minus alpha, because if I do this, then alpha minus 1 will be 2 minus alpha minus 1, which is 1 minus alpha. So, doing this transformation, I have to do this one. So then, if f of alpha is literally rewritten from here, so it is alpha q plus 1/2 is q small, and then this tau of q, which is minus tau of q, which is minus q plus 1/2, and then and then plus this thing. So it is just rewritten this relationship or this relationship, just rewritten in new way. But now I use this fact that 1 minus alpha is odd in Q. So as I said, 1 minus alpha odd means that if alpha is replaced by 2 minus alpha, then q should be replaced by minus q. And this is what I'm doing. So instead of alpha, I write 2 minus alpha, then again here 2 minus alpha, and instead of q minus q. And here also q minus q. This is unchanged, and instead of delta of q, I should write delta of minus q. But delta of minus q is equal to delta of q. And then if I subtract this thing from that one, this delta of alpha cancels out. This unknown delta of alpha cancels out. And what I have is a simple combination which you can do this subtraction and you obtain this relationship. F of alpha minus f of 2 minus alpha is alpha minus 1. So this is another manifestation of this symmetry in the alpha picture. So you see, it is not very trivial. It's not very trivial. Now I tell you a bit more. So first, this symmetry was, as I said, discovered by Milne and Fedorov for 3 Dyson symmetry classes. But then people try to generalize it, saying that, well, maybe the relationship like this with some q star instead of 1 would somewhere hold. And it appears that indeed this is so. And you know, again, looking at all this topology of the Q matrix, one can say that independently of anything, so if your physics is described by the signal model with this topology of the Q matrix, which was derived by Yefetov and then followers, then for all the Dyson symmetry classes, this is 1, and then there are 2 other classes of the classes that I gave you, where also independently of whether it is localized or it is multifractal or it is extended or it is any dimensional, there are 2 classes where this Q star is 2 for one class and 3 for the other. So those classes are these superconducting symmetry classes. They are in the table that I gave you. Oh, so many of things that I cannot find. Yeah. These are 2 symmetry classes. One is this and the other is this. So you can see what it corresponds to in terms of symmetry with respect to time reversal and with respect to Pachko hole. but all those symmetry classes somehow related with superconductivity. So they are classes which are realized in various cases of superconductivity. But the classes which are not related with superconductivity, with particle hole symmetry or with Bogoliubov-Dijon equations, are the chiral classes. So there are three Dyson classes, and there are three chiral classes where chiral symmetry works. And so basically these three classes and those three classes are close relatives. And for those three classes, the situation is more complex. So the symmetry of Q matrix is not enough to judge what will be this Q star, and let me find first. Okay, so for the chiral symmetry classes, for the three chiral symmetry classes, situation is complex in the following way. So, as I said, these numbers do not depend whether it is localized files. Okay, so I'm sorry, in localized phase, you have. I'm sorry. So let's not talk about the localized case. Let us talk about the extended case. So, but it doesn't matter if it is an extended case of which dimensionality you have, and all details of the system does not matter. What matters, if you can derive sigma model, then you are done, and then you know this Q star for these 5 symmetry classes. But for the chiral classes, which, as I said, are close relatives to this, the situation is different because this Q star depends on details of the system. So you can have, it may depend on dimensionality, it may depend on the distribution of disorder and things like that. So it is not universal. But anyway, if you have such generalized symmetry with some Q star, then doing the same manipulations as I did before, you can generalize your symmetry for f of alpha. So the only thing is that alpha minus 1 was multiplied by 1 in Dyson symmetry, and here it is multiplied by Q star. So this is the same derivation as here. So the only thing is that you should write here Q star over 2 and not 1 over 2, and then everything else goes in the same way. Okay, so so this is, as I said, this symmetry is extremely non-trivial. And now I show you results which actually are from our paper on random regular graph, the paper of 2014, which had a lot of discussion, a lot of criticism, and so pro and contra, and now everything settled, I would say, and I can tell you what is going on. So what is the random regular graph? It is a graph endpoints, and they are arranged in such a way that any point is connected with a fixed number of others. So here it is connected with 3. Now this thing can be very roughly viewed like this. So you have a Cayley tree, and then you connect the leaves, the boundary of this tree, such that big loop appears, but locally it is like a tree. And here you cannot really see that it is locally like a tree, but it is the case. So if you study more precisely this graph, you will see that it is locally like a tree, but then these leaves of the tree are connected. So why such situation is, why such graph is studied instead of the tree? The thing is that the tree is a pathological structure because it is not statistically homogeneous, because there is a root, there are leaves, and statistics is different. So you cannot say that, let's say, psi squared is average is the same for all of them. But if you pass from the tree to such a structure, then in this structure, any point is statistically equivalent to any other, because from any point there is a growing tree, and then it is closed by big loops. And so statistically this is a homogeneous, like a lattice. So it doesn't have a boundary. And the tree has a boundary. This is the whole thing. The tree has leaves, the boundary, and on this boundary there is a finite fraction of all the sides, so 1/2. And therefore you cannot neglect this boundary. So if you are in infinite dimension, you may say that the fraction on the boundary is always decreasing as the size of the lattice is increasing. It is not the case for the tree, because on the tree, whatever is his side, let's say half of the sides will be on the boundary, and this is more like a lattice, because here every point is statistically the same as any other. And then there was a question how, what is f of alpha? As I said, you can do exact diagonalization, and you can find the distribution of psi squared, and then you can plot this f of alpha and n, which is the other representation of this distribution. And this is the result. So, you know, it was already 12 years ago, and computers were not as powerful as now. So we did modest sizes by today's view. It was 4,000, 8,000, 16,000, and 32,000 only. Then you do exact diagonalization, you find distribution of psi squared, you draw this f of alpha n. And you see it evolves somehow with n. Now, when you look at any finite n, you see that the exact properties of f of alpha are violated. For instance, the maximum is not at 1, and then if you look at this Millen-Fedorov symmetry, any of these does not obey this symmetry. But then what we did the following: take any alpha, and so you have points, this one, this one, this one, this one, at a fixed alpha, depending on n. Now we plot these points as a function of 1 over logarithm of n. So 1, 2, 3, 4, there was another one, I did not show it here in order not to make too dense picture. So you have points like this. It is f of alpha n at a fixed alpha, depending on logarithm of n. And you see that they are approximately lying on one line. Then what you can do, you can make a feed, a straight line feed, and see where this straight line hits the y-axis, and this will be corresponding to logarithm of n equal to infinity, and if this tendency then continues, then it would be an extrapolation of f for a particular alpha. And then you can do it for many alphas, this procedure. And what you get this red curve. So you see, this red curve is much closer to what is required for the for f of alpha. So the maximum is a bit higher than 1, but very close to 1. And then one can check Millen-Fedorov symmetry. So this Millen-Fedorov symmetry, in order to memorize, it is.
What is the red line?
Huh?
What does the red line corresponds to? What is n size or
Say it again.
what does the red line correspond to?
The red line corresponds to the following. So you take alpha, you find 4 different points,
Yes.
okay, and then you make a linear feed,
Yes.
and then you find the point where it hits the y-axis. It corresponds to 1 over logarithm is equal to 0. So it should correspond to the limit and goes to infinity. And you put for this alpha, you put the corresponding point, and this will be the red line. For any alpha, you have this intersection. And so
you have
when
two,
plot it,
2 dots.
Huh?
You have 2 points. You're certain.
I have to make sure that this tendency continues. Nobody can make sure, because it is, it is a shooting,
The question was this red line plotted by these 2 points. You let's say no, because of one point is intersection, and the second point is the maximum that you.
No,
that you obtain from this.
I mean, this red line is drawn without any. The only assumption is that this fits. So, for instance, if I take this alpha, I have this point, this point, this point, and this point. I put it here, and then I make an extrapolation. And then I take this point and put it, and so for any point. So I didn't do any assumption except for this straight line. Mm-hmm. And of course, when you are shooting at such long distances, you could miss the target, right? So nobody can tell you that you really are here. But then, but this is what was done. So the first thing was that that the resulting curve, it is far from this. It is far, but it is closer to what requires from the fractal f of alpha. Now, then the next test, much more sophisticated, is the following. You take this Millen-Fedorov symmetry, and Millen-Fedorov symmetry is f of alpha minus f of 2 minus alpha is alpha minus 1 or 1 minus alpha. I remember it, not to memorize, I remember it like this. I shift alpha, and f of 1 plus alpha is equal to f of 1 minus alpha plus alpha. This is just shift of. And here it is exactly what was done. So first we plot f of 1 plus alpha. It is a blue line. So you take this red one, so forget about this, you take this red one and plot it like this. And then you take the same red one and plot combination like this. So if Miller-Fedorov symmetry for this red curve is okay, I should have these two coinciding. And what? This is the result. So you see, we just did an experiment. And then when I saw this thing, and it was not only, it was for several W here. So here it is W10, then there was W7, W12, more or less the same thing. And then we published a paper that for random regular graph, there is a fractal state and multifractal state. And then it was criticized because if you take sigma model and then also make some approximation to this model, some saddle point approximation, you will get a different result, that your all your fractal dimensions are equal to 1. So how to reconcile these two? Reconcile these two is to say, well, in fact, when as I go for larger and larger logarithm of n, something happens, and these things start to deviate. So it was first like a straight line, and then when I have no control, it starts to deviate and goes to 1. Okay, believe you or you don't believe, it is like this. So the thing is that this was just a numerical experiment. But what I want to tell you is that this symmetry, Miller-Fedorov symmetry, is very non-trivial. And the curve itself is not trivial. And when it coincides like this should mean something. And what the simple thing is to say, well, this is the proof that that there is in n equal infinity. This is the exact f of alpha. It is a regular function, not just some straight line, and this tells you what is a very large n, which you never access by exact diagonalization. The fact that this Miller-Fedorov symmetry is fulfilling here with such an accuracy, for me personally was a likelihood that it is indeed so. But sigma model gave something like this. And since sigma model proved to be the most advanced theoretical tool, then all the theories which believe in theoretical tools and not in numerical experiments, they say, well, okay, so, but sigma model tells that eventually it will go to 1. What I can say now, I think that this is nevertheless is not accidental, because if you take any of these curves, the coincidence will be very bad. So there will not be symmetry. The symmetry appears only if I do this logarithmic extrapolation. And now I think that this question is still open. But as the very minimum, I think that what happens is that there are, if I want to reconcile what Sigma model says and what this thing says, I have to mention something like that there are two legs. So one is smaller and the other is larger. So for instance, one, and then, so if I take logarithm n and say that there is some length, L1 and L2, such that if your system is smaller than this, then you have things like that. So you do not have symmetry, you do not have f of alpha required. So here the multifractality is not set in. And then after L1 there is at least finite size why I am saying finite size multifractality. I am saying that for such lengths you already have things close to this red curve, and then you have a symmetry and all these things. So if you look at if you could reach such length larger than L1, then you would find some fractal state which you would not really distinguish from the true one. But if the sigma model consideration is true, then there should be other lengths, and when you cross these other lengths, then this nice picture is destroyed, and this curve, until this curve goes, presumably L1 is quite small, then I'm always in the region between L1 and L2 when I'm on this straight line, and then something happens and it starts to go up to 1. So this is a scenario, nobody's scenario, if you believe that that sigma model is giving. It is not an exact solution of the sigma model. It is some saddle point approximation which nobody knows if it holds true or not. So then there is a very recent development, and this very recent development actually raises question about sigma model even more, because this was the random regular graph. But there is a relative of this random regular graph which is called ER graph, so René and somebody else. So this is the graph in which this coordination number, the number of connections from one side to the others, it is not fixed. It is fixed only on the average. This problem was considered by the same Milin and Fedorov in the 90s. And they considered it exactly by the same method as they considered this random regular graph. So it was the same saddle point approximation and things like that. And then they arrived at a statement that, again, there is only ergodic phase, and and then localized, and at the critical point there could be a critical state, so not could be, but they are, but no phase like fractal phase. Because what I'm saying by phase, in the Anderson model there are fractal states, but they live only in one point, in the critical point. If size goes to infinity, if size is finite, then there is some region where they live. But phase is when fractality lives in some region of parameters, so not going to zero and then goes to infinity, some fixed region of parameters. This is the phase. And what they found for this ER graph, which, as I said, it is only different from this problem by two things: that the coordination number is fluctuating, and second is that the strength of the link of the hopping is Gaussian distributed. And what we found is the same as for RFG, but recently it was, I would say, proven to be incorrect for this graph. So I have to finish because people are waiting. So I will probably, and this is very recent thing, because this paper where it was proven that it is incorrect, it is a paper by Letizia, Curiandolo, Venturelli, other things, other people from Trieste and from Paris, and they did some numerics which are different, which are not exactly diagonalization. So if you will have time, I will probably say something about this thing. And now the situation is such that by the same method of the same treatment of sigma model, it was proven for this ER graph that there is no multifractal phase. And a recent paper demonstrates that that there is. So then, you know,
Vladimir, last time you mentioned some paper from Google where you said they investigated. Last time you mentioned some paper from Google where they investigated.
No. It is not a paper from
No,
Google.
last week.
It is a paper by of 2024. Curiandolo is the first author.
No, I understand, but last week you mentioned for the f functions and for the
Yeah.
vector
They have the same thing. So
yeah, but I didn't find this article. Can you maybe
okay,
let me know?
Let's let people go. We will discuss.
Okay, yeah, good.
Thank you.